Section 3.2 now. I'm going to talk about some measures of variation or dispersion of data. Okay, now coming from section 3.1, we talked about measures of central tendency. More specifically, we talked about mean, median, and the mode. And I did mention in the video in that section that we're going to stay with the mean, the arithmetic mean, although it's sensitive, but we're going to take that with us to future sections and chapters. Well, this is the one section that we actually will carry the arithmetic mean with us. So, in section 3.2, let's talk about measures of variation. Now, when we talk about variation, we're talking about spread of data points with respect to some other measure. Okay, how the points spread out. Well, we can do a dot plot, right? We've seen dot plots before. And the dot plot actually shows a visual, gives us a visual of the spread of our data points. But we would like to be able to quantify them and put them in terms of numbers, how dispersed the data is. In this section, we're going to talk about two measures of dispersion. One of them is range, and the other one is going to be standard deviation and or variance. Those two are very closely related. So, the easier of the two is range. So, what do we mean by range? Well, range is given as the difference between the highest and the lowest score. That's all that is. Okay, so we have the highest minus the lowest score. I've made up 2, 4, 6 numbers here. Suppose I have a sample. These are the weights in kilogram of 6 randomly suitcases at an airport luggage area. Okay, so these are in kilograms. There are 21 kilograms, 26, 23, and so on. The 23 kilogram is roughly about 50 pounds. Okay, the weight limit for most airlines. Okay, now for this one, we want to calculate the range of scores. So the range of scores, I just need to subtract the low from the high, which is 28, right? The high is 28, and the low is 21. So 28 minus 21 is going to be 7 kilograms. So we can say that the data lies within a 7 kilogram range, going from low to high. Okay, now the rest of them, I know they're not ordered, but even if you order them, 22, 23, 24, 26, that's not going to affect the range. Still low minus high. Okay, so there you go. This is something that's, I guess, useful. Usually we would like to have a small range. Imagine if I said that the range of weights of suitcases were 15 kilograms. Well, that's a wider range, 15 kilogram, as opposed to, let's say, the current range of 7 kilogram. That means there's lesser of a spread in the data. Okay, and we like smaller the spread, the better. That's what we like. So that's one measure of variation. We're not going to do a lot with range again going forward, but it's a measure of spread of data points. Okay, now let's take a look at the range right in here for our exam scores. The high score was 99, the low score was 35, so the scores are in a 64-point range, rather large range. Now, here's one thing though, that it's a big disadvantage of the range. It only uses 2 scores. Okay, so let me find these low score. There we go, the low score is here, and it happens to be right next to it is 99. Now, if there are more than 199, then you can choose any of them, but there's only these 2. I have 135 and 199. Now suppose, because range only uses those 2 scores, right? And suppose you didn't have any of these. Now, so you can just there you go. If I just gave you those 2 scores, could you tell me anything about the scores, the other scores? I don't think we could, right? Because we're not looking at them. We don't have them. So if these are exam scores, I got the low score 35, someone else in class got 99. How did everybody else do on the exam? We don't know, simply because there's a lot of confounding here, right? Because we simply don't know. So that's the drawback of the range, is that it really doesn't tell you much about the other scores. If my score was a 10, the high score was 100, how did the class do on that exam? I don't know. We don't know. So that's why we don't really use a range directly. Sometimes range is used in conjunction with other information to kind of guesstimate the standard deviation. And to do that, we usually divide range by 4, and that gives us an estimate of a standard deviation. Okay, so now let's actually take a look at the next measure of dispersion, namely standard deviation. Okay, now to motivate the standard deviation, suppose I'm making up 3 scores. So I have x sub 1. We're going to make it easy, okay? 10, x sub 2, 15, and x sub 3 is 20. Now I just made these nice round numbers, but what we're about to see, what we're about to do and witness, has nothing to do with the way I've selected these numbers, okay? I'm selecting these numbers for simplicity for now, okay? So hopefully I don't need a calculator to do anything with them. All right, so that's my intent. Now let's take a look at the average. First of all, let's find the sample mean. Remember, x bar, the sample mean, is sum of the x's divided by n. So that means you add 10, 15, and 20. What are we going to get? 45 divided by 3, and the average is 15. Okay. Notice we use average before, and it is now here again. I'm going to go ahead and plot these points now. Okay, so the center of this data, although sample is extremely small, but it illustrates our point, is 15. That's x bar. Now x sub 1 is 10. This is a numbered line. Okay, so let's say here is 10, 15, and this would be 20, and so on. 20, 25, and blah blah, and there's 5. Now a score of 10, I'm just gonna write it like this. You can put a dot, like a dot plot. I'm using square, so that's where 10 is. The second observation is 15. That's exactly 15. It's what the average is, right? Okay, and 20 is the next number, so here's 20. So I've plotted those what do you call it, those 3 points. Now if I look at the dispersion, okay, the dispersion that I see from 10 to the mean. Okay, remember the mean happens to be 15, which is this value. It's purely coincidental. But if I look at the dispersion of 10 from the mean, that's the dispersion or deviation of 10 from 15, isn't it? Now that deviation, we're going to call it 10 minus 15, or negative 5. The negative, what's the interpretation of negative here? That means that score is 5 units below the average. A negative deviation means you're below the average. A positive deviation means the score lies above the average. And by the same token, if I look at the dispersion of 20, well, 20 minus the mean is 5. That's positive, and it lies above it. Now 15 itself, the score of 15, if you do 15 minus 15, you get 0. That score has no dispersion because it is the mean. So it's a 0 deviation from the mean. So what we've done in effect right now, I found these 3 deviations, a negative 5, a 0, and a 5. We're going to call this x minus x bar a deviation from the mean. Okay, that's what we're going to call it. Now, let's say I have 3 deviations from the mean. Just like I have 3 different numbers, I have 3 individual deviations from the mean, a -5, a 5, and a 0. And the question might be this: what is the average deviation? I know I have some that are higher, some that are lower, and some are exactly 0 in a bigger data set. So how do I calculate the average deviation? Well, just as with any average, I'm going to add the deviations, -5 plus 0 plus 5 divided by 3. And that's going to give me 0, because -5 plus 5 plus 0 is 0, divided by 3 is 0. So the average deviation ends up being 0. That means on average there is no deviation. Now, something interesting happens here. Okay, that interesting thing that happens here is the following. I made up these 3 numbers, and you can try this. Make up any number that you desire, any number. Make it 1,000, 200, 179. It doesn't matter. And it doesn't have to be 3 numbers, by the way. It can be, make up 50 numbers, any number you like. Ask your friends to give you numbers. Okay, random numbers. And then just do what I've just done, and you actually find something very fascinating, very interesting happens. Okay, and this is what's going to happen. See, the average deviation is 0. The reason that was 0 was because the sum of deviation was 0, wasn't it? So we're going to generalize this. In general, this is what's going to happen. I'm just going to write it as a note. The sum of deviations from the mean is always 0. Okay, so actually this creates a dilemma for us now. Why? Because if I do this for everybody's data set in the world, we all gonna get 0 always. So if we rely on just this, then there's really no use for it. It's not useful at all. When every time, predictably so, the deviation, the average deviation, ends up being 0. So let me write that now symbolically, what I just noted. And the sum of, remember those 3 words, means sigma. Deviation from the mean, well, deviation from the mean is that. So I'm just going to go x minus x bar is always 0. So we're going to take that to be a fact. Okay, on face value. And I'm just going to say for all x. Okay, so some of these deviations from the mean always going to be 0. Now, we need to work around this. Okay, how does the workaround work? Okay, and one way to do this is to look at absolute value of the deviations. And if I do, the negatives become positive, and then I can average them that way. They're no longer 0 if I do that. In fact, that's one measure of dispersion, but I won't mention it because it's not in your book, but it's out there. The other corrective action we do is this. We can actually square the deviations now. We're trying to get around this deficiency that it's always going to be 0. That's what we're trying to do. So our way of doing it is the book's way, is most people's way of doing it. We're going to square the deviations and then add them up. How's that? So I'm going to do that. I'm going to square the deviations and then we're going to add them up. All right. Now, if I square the deviations, then I'm going to get -5 squared plus 0 deviation squared, still 0, and a 5 squared. That total is going to be 50 now, right? 25, 0, and 25 makes 50. So what is this now? This is sum of square deviations, right? And if I divide it by the total, that's 3 deviations, right? because I have 3 individual deviations. So this is going to be 50 divided by 3. And that's going to be what, about 17? Because 17 times 3 is 51. It's going to be 1/3 shy of that, right? So 50 divided by 3 ends up being 16.7. All right. So that's going to be now the average squared deviation. That's what we're going to call that. This quantity is, that's 16.7, is what we call average squared deviation. Now, the trouble with this number is just that, because it's in squared form. What that means is this. Let's say this data represented dollars for something. These are the prices of 3 items: $10, $15, $20. So the units on sum of a square deviation, if these were in dollars, the units on this will be dollars squared. Now, question is, how do I interpret dollars squared? Or if I'm looking at, for example, these are the time it takes for a student to complete an exam. Let's say the square deviation, average square deviation, ends up being 20. That means 20, let's say, minutes. 20 minutes squared. Again, that doesn't make sense. So, how are we going to interpret this thing? We're not going to interpret this at all. So what we do, in fact, is we take the square root of dollars squared and puts it back in dollar format, right? Now we understand what dollar is, but we don't know what dollar square means. So this suggests I need to take square root of 16.7, right? And when I take the square root of 16.7, that number turns out to be about 4.1. Okay, 4.09 to be more exact. Now this would be in dollars. So let's say I bought 3 items from a shop. I bought something for $10, for $15, for $20. The standard deviation of those 3 items I bought is $4. Okay. Now, what does the standard deviation tell me, by the way? The standard deviation at this point, we're going to call it the give or take. The give or take for the measure of central tendency. Okay, because it's found about the center of the data, so that's how we're going to interpret this. So in other words, on average, let's say I went to a shop and I bought these 3 items. And I can make this statement as following. I can say the average person in that shop, based on myself, the average person in the shop spends on average, that would be X bar. Or X bar was, did I ever find X bar? Yeah, $15, remember, made up. On average, the person spends $15 in that shop, give or take $4. That's what standard deviation is. So for standard deviation, we translate that into the give-take portion of our data. All right, and that's what that is. So now let's formalize our formula here. Okay, now to formalize the formula, here's what we just did. We did sigma x minus x bar squared, and we divided it by n, didn't we? Now, here is a, I hate to say this, but this is kind of like magic, something that we need to do. Rather than dividing sum of square deviations, right, the numerator, by n, the sample size, because there are n deviations, we're going to divide, let me just say, use this formula. We're going to go sigma x minus x bar squared over not n but n minus 1. Now, why do we do that, right? Well, there are several reasons that's cited for this. Let me just give you the easy, the non-mathematical way of saying this. The reason we do this is because in our inferential statistics, when we generalize to the population, it turns out that if you use this number for the sample, it underestimates its counterpart in the population. Okay, the quantity that's before you right now that you're looking at, this is called sample variance. So its counterpart in the population is going to be population variance. So this number, based on the formula above here, this one, I can write it now. This one that's up here, this underestimates population variance. Now that I mentioned the word variance down here. Okay, so if we don't want to underestimate population variance, then we need to divide by n-1. So that's, in that sense, it's mathematical. Notationally, we're going to use S for like sample, S squared, superscript 2. So the square here on S, this is a reminder to us now that these are square deviations. So sum of square deviation divided by n-1. This is going to be the formula for our sample variance. Okay. Now, if we take the square root of this number, remember, we had to take the square root up here, in here, right, to bring it back to the original units of measurements or scale of measurements here. So if I take the square root of this number, square root of sigma of x minus x bar squared over n-1, we're going to call this sample standard deviation. We know what a deviation is, right? A dispersion or spread. So it's a deviation. Standard deviation, think of a standard as a normal, typical, something you set the standard for everything else, you know, in that sense. So we're talking about a typical or a normal deviation, right? What's typical? What's the norm here? So that's what's the standard. So the standard of the deviation is going to be that. All right. Now, again, we can do this by hand, but going forward, we're not going to do this by hand except one time later in chapter 10. We're going to use this formula in chapter 10. And when we get there, I'll remind you that we did this in chapter 3. So now I can actually flash these formulas for you. This formula is for S squared, and the other one is for there you go, that one is for standard deviation. Okay, and both of those I have them handwritten so you can see what they look like. All right, now StatCrunch does this for us, by the way. Okay, so let's go to StatCrunch and actually do one for our example that we just did. Okay, the test scores. I still have that data in StatCrunch. So let's do that. I'm going to go back to my MATLAB here, okay? And there you go. The data is still here. Perfect. Now, for this data, let's find sample deviation and sample variance. That's all we want to do. Oh, and range. We talked about those three things, right? So let's do all three. So I'm going to go to stat, summary stats, columns. Okay, because again the data is in a column. And then once I'm in there, click on the columns and select a variable, left click once, exam. Now remember, down here is a list. I'm gonna left click once on N, and remember what we had to do here, right? We had to click and hold, right? We're going to click and hold, or shift and hold. I'm gonna do control, click on variance, and click on STD DEV, standard deviation. And let's scroll down slowly. I'm still holding the control button right on the keyboard, don't let go, and click on range. And those are the three things that we talked about in our section on dispersion. We talked about range, deviation, and variance, and hit compute, and there you have it. So for the exams, for the scores that you're looking at that are on the left, okay, right in here, for these scores, the range ends up being 64. I guess we verified that. That's the high minus low. That's 99, or yeah, it was 99, and the low was 30. So what was 35 was the low score? Let me see. 333, yeah. 35 is the low score. So the range is going to be 99 minus 35. And that's going to be 64. Now, the formula for standard deviation variance, if you do this by hand like I did with the others, that's what you got to get. Keep in mind, please, we want to use the StatCrunch. We want to use technology. We don't want to do this by hand as much as possible. So, and we're not going to be doing this by hand in the future chapters, so I don't want you to waste your time trying to do this by hand. Okay? Well, let's do it in StatCrunch. And there you have it. So if those were exam scores, a typical exam score here, say 16.18, so the typical average, remember we found the average to be 77.5 from before. It's still here, my session. There you go, summary stats for exam. Let's put them kind of side by side, and you'll see this, right? We found the mean to be 77. So the typical score on that exam is 77.5, give or take almost 16 points. Give or take 16 points. So that means if I'm taking that exam myself, okay, if I'm taking that exam, I would expect to get 77.5 on the exam, give or take, plus or minus 16. I'm just rounding this, 16. And in fact, the 77.5, let me round that also to, how about 78? Okay, so let me round this to 78. Here's 78, give or take 16. So if I add 16 to 78, I get 94. If I take away 16 from 78, that would give me what, 62? And there you go. This is how the mean and deviation now work in tandem together. One gives you the expectation of what you would get on the exam, and the number next to it gives you the expectation about the dispersion, give or take, as I called it. So I expect on that exam, if I'm an average student, okay, if somebody's really smart, they can do much better, or somebody's not so good, they do much worse. But if I am the average student, I would expect to score anywhere from 62 to 94 on that exam. Okay, so that's what we're going to call it. And that's all we wanted to cover in this section. Okay, so we're done with this work. Let me go back to my note. So again, in this section we talked about measures of dispersion, and with measures of dispersion we talked about the range. Let me go back up. Yeah, we talked about the range, and we talked about the variance and standard deviation. These are all from the sample. Okay, so hopefully I was able to explain things for you to a point where you could follow them and understand them easily. And with that, we are done with this section.